guys, a very happy morning to every one of you. And guys, now we are just going to see the next thing in the strength of materials. Okay, so without wasting time, let's get started. So at the first, I'll just basically explain each and everything. And the torsion means it is just a simple thing, not a very complicated, not a very tough thing. So just to take a shaft, it means consider this as a shaft. The shaft is rotating clockwise and anti-clockwise, and during its rotation, how much the shear stress will be, how much the torsion will be, how much the modulus of rigidity, and each and everything will be. That is the only thing we are just going to see in this chapter. Okay, so you can see in the torsion. In machinery, the general term shaft refers to member, usually circular cross section. I'll just zoom a little bit. So you can see which supports the gears, sprockets, wheels, and rotors, and which is subjected to rotation, torsion, and transfers or load acting on a simply or combined. Okay, so it's generally a simple thing. And just 1 second. Perfect. So an axle is a rotating or non-rotating member that support wheel and pulley and carries no torque. Carries no torque is an axle. Spindle is a short shaft. It means a short shaft termed as line shaft, head shaft, or stump shaft and transmission shaft. Counter and flexible shaft, which are named in the different ranges. Okay, so generally the formula is tau by r, t by l, t by g, zeta by l. Okay, this is the basic thing. Okay, so you can see J is a polar moment of inertia, tau is a shear stress due to torsion, and G is a modulus of rigidity, and theta is a angular deflection of the shaft, and R and L is shaft radius and length respectively. So assumption the bar is acted upon pure torque. Okay, the entire bar is acted on pure torque. Okay, so the section under consideration is removed from point of location, point of application of the load, and from the change in diameter. Adjacent cross sections originally planes and planar remains plane and plane after switching. Definitely this material obeys Hooke's law. This is one of the most important things you just want to do. Okay, and you can see cross section rotates as it is rigid, means every diameter rotates to S. Definitely you can see, guys, if it rotates, I think so you can see. So whenever the torque is applied, you can see angle of twist is being there, and as well the rotation also differs. Okay, due to the rotation difference also each and everything will be different. Okay, you can see this is applied torque. So you can see here each and every plane is important. Okay, X plane, Y plane, Z plane is important. Polar moment of inertia J equal to 0 to R 2 pi R cube of dr. Okay, 2 pi, okay, 2 pi R cube of dr. Okay, J equal to what? I'll just write it down. J is a simple thing. J equal to integration of 0 to R 2 pi R cube of dr. Okay, this is the most important thing. Okay, for solution point we just make the integration by d power 4 by 32 will come. Okay, for hollow shaft pi by 32 d power 4 minus of d power 4. Okay, capital D power 4 minus of small d power 4. I think so. I hope so you understood. You can see for solid shaft. So okay, so what is the Z? So Z equal to J divided by C. Okay, so while you are calculating, this answer will come. Okay, this is not that much. Okay, anyways, I think so you can't it means you understood. Next one, power transmission P equal to 2 pi n t divided by 60. Okay, 2 pi n t divided by 60, and whenever in HP you are given, you can see HP is 75 kg meter per second. Okay, 1 HP is 75 kg meter per second. So put here, so multiply of this thing, we will get the required answer. Okay, I think so got the point. This one, okay. So this one, as the video procedure, I'll just explain each and everything. So next thing we just so you can see tau by r equal to T by J equal to G theta by L, okay. So tau equal to dr divided by J, okay. So whenever it means you can see this is the entire thing, means guys simple. Suppose you can see here the torque is applied, means it's been rotating. So here definitely the radius also will rotate, the theta will rotate, and each and everything will also we see, okay. So you can see diameter equal to 100 millimeter and the torque given is 2000 Newton meter, okay. J is polar moment of inertia 7.4. So we can easily calculate with put here the shear stress, you can easily calculate, okay. So what is the shear stress applied on each location? It is this shear stress tau into radius divided by J. You can see the radius this side is this one, okay. If you just put r equal to 0, the entire shear stress will be 0. So same like that, okay, like this, okay. So here you can see the entire shear stress is 0, tau equal to 0, okay. I think so just a simple thing, and I convention. So the entire thing like this will be shear stress 0, and while it's been shear stress little bit increase, little bit increase, what is maximum like that, okay. So just a simple thing, okay. So to equal to T, so it's a basic formula, and radius is the shear stress also changes, okay. So section hollow, it means circular cross section. You can see this is the outer diameter D and internal diameter small d, okay. So what is the polar moment of inertia? Pi by 32 d power 4 minus of d power 4. It means capital D power 4 minus small d power 4. Okay. So you can see shear stress, so each and everything is same, okay. Radius, everything. So in this entire thing, basic thing only we just need. Suppose if you just understood the basic, each and everything will be clear cut for us, okay. Next one, polar moment of inertia. This polar moment of inertia geometric property, okay. Polar moment of inertia geometric property, okay. Depends on shape and size, okay. So Zp equal to J divided by R, okay. What is polar moment of inertia? J divided by R, okay. So J is, I think so you can understand. So if tau equal to J divided by R, okay. So you can see if this shear stress equal to torque divided by Zp, okay. You can see if Zp increases, shear stress decreases, okay. If polar moment of inertia is high, the shear stress leads to decreasing, okay. So we need only torque, and we if some load added, then it becomes combined load, okay. We just need only torque. Yes, definitely if torque plus any kind of other load is been added, it comes going to get a combined load, okay. So you can just see the first question. You can see this entire thing, okay. They just ask the shear stress, okay. Suppose if they are, you can see this is a, it means for solid this is a basic formula. It means each and everything is J equal to pi d power 4 divided by 632 and radius equal to d beta. Each and everything we are applying under the formula for the solid, okay. Shear stress for solid equal tau equal to 16 T divided by pi d cube, okay. Tau equal to 16 T torque divided by pi d cube, okay. So same thing, tau equal to this one T r divided by J for hollow shaft, you can see T into d by 2 divided by pi by 32 d power 4 minus small d power 4. So you can see 16 T d divided by pi d power 4 minus small d power 4, okay. I hope so understood. So you can see tau 16 T divided by d cube, okay. So you can see tau equal 16 to everything. So in the question they would have given about the diameter and the shear stress. You can easily calculate. This will just tell you later. What video, okay. Alright, just the basic thing. So let us see. So you can see here the entire equation is given like this, okay. Like this is being given, okay. Torque, okay. Torque is kilo Newton meter divided by meter, okay. So they are asking the where is tau maximum. So definitely at the end only the here the end only the tau maximum side. Okay, so suppose if you can see x equal to 0, this x equal to L. Okay, so tau maximum will be, what is the formula, 16 t divided by d cube. Okay, so you can see what is torque equal to this t into total length. Okay, 16 small t into L divided by d cube. Okay, I think so you got the point. So the next thing is, suppose this one we just got, and the other thing is, you can see whenever it's been twisted, suppose we are just giving one angle diffraction means just one twist means it is easy to calculate, but you can see it's been multiple, so we don't know where the theta will be. Okay, it is, so that's why it is go little bit difficult to calculate. Okay, so that's why we go for the distance and we calculate the theta. Okay, d theta equal to TL divided by g of j. Okay, d theta integration equal to this entire thing, so it means TL divided by j times is t of x into of dx divided by g of j is by d power 4 divided by 32. Okay, integration, so calculate, it means is x equal to 0 to x equal to L, well we are just calculating theta equal to 16t L square divided by g d power 4. Okay, this for UDL, uniform distribution load. Okay, next one you can say, this is based upon torque diagram, we are calculating this another thing. So you can see here 900 Newton meter is cost length. Okay, and this side is called 350 nanometer, and you can see after going certain 4 feet downwards. So this is generally a torque diagram. So response power transmitted by the shaft equal to what will be tau max equal to dr divided by j. Okay, so power equal to torque into omega. I hope so understood. This is a basic question, so I'll just explain the questions later on, but I think so you understood the concept. Next one is shaft in series. Okay, series means this is a series. Okay, so I think so like this. So you can see whenever we just apply the torque, what will happen, this will change to a theta 1 and this will just change to a theta 2. This will rotate so much and this will rotate so much lesser. So theta equal to theta 1 plus of theta 2. Whenever the torque is applied here in this location, you can see this dominates the move. So theta equal to theta 1. Okay, and it means this rotates for 5 degree, means this one also rotates 5 degree, because we are not applying the torque here, we are applying the torque here. Okay, I think so you got the point. So next, torque in parallel. So like this, so you are rotating means here theta equal to theta 1 equal to theta 2. Okay, I think so you got the point. So next one, here the torque will different, T1 plus of T2, the torque will different. Okay, I think so you are able to see this one. Okay, I'll just I think so you can see this one. So you can see here theta is been same, but you can see the torque will differ. Okay, I think so you got the point. This is the extra question, I'll just tell you later on, and whenever it comes to the whenever it comes to a stiffness case, what is stiffness? Stiffness is K. Okay, K equal to P divided by deflection, load deflection. Okay, this is the thing, and same as this is the PA square. Okay, so based upon this we can just calculate each and same way for the torsion difference, KT equal to torque into theta. Okay, this is Newton meter per radian. Okay, KT equal to torque into theta, Newton meter per radian. Okay, this one is 100 in series. theta equal to theta 1 plus theta 2 plus theta 3. Okay, each and everything you just rotate. Okay, so next one we will be seeing the combined load. Okay, so combined load first type 1, only torsion plus a bending moment. Okay, torsion is given as well as bending moment is given. Okay, so like this, and the moment is given like this, and moment is given like this, and torque is given. Okay, T. So this is a thing which means like this. Okay, I think so. So only torque plus a bending moment is given. Okay, suppose if yes, definitely. Okay, so you can see this one. Okay, how the thing will be here. The maximum torque is there. Okay, shear stress equal to 16 T divided by pi t cube. Okay, this is solid. Okay, you can see this is the entire is tau max, and the shear stress sigma. What is the shear? Elizabeth Rani, may I help you? Okay, sigma equal to my divided by I. So you can see maximum stress will be 32 m by d cube. Okay, this was solid at the outline. Okay, and at the bottom it will be most of compression. Okay, the simple thing guys, if I just given the chapter like this, bending moment given, you can see here the tension will be, here the compression will be, that's why it will be given minus. Okay, so I think so you can understand. But at the both of the time, at the neutral axis, at the center axis, everything will be the bending stress will be 0, the shear stress will be 0. Okay, I think so you got the point. So this is the axis of the shaft. So like this. Okay, so this is center axis. So this is axis of shaft. Okay, longitudinal axis. So the same times it means the upper it means like this. Here what will be, here the shear stress will be shear stress plus of bending stress, but here the shear stress minus of bending stress will be. It is how to say, but at the middle portion it is entirely 0. It means shear stress 0, and wait. Okay, at the bending moment shear stress also 0, and as well as the bending stress will also be 0. Okay, so you can see here this is the entirely principal stress 1, this is entirely principal stress 2, and shear stress and each and everything is been there. So it is complex state of stress. Okay, I think so about the one. So you can see this one. So this is the entire thing. Okay, so you can see this you can get under here. You can see all critical point we just added. Okay, all critical point it becomes critical fiber. So if at the outer if at the outer surface it hasn't failed means, then at the inner surface failure doesn't occur. Okay, critical point, critical cross section and critical fiber will come. Okay, so this is the basic thing. Okay, see this is a torsion each and everything, bending stress everything calculated. Okay, just a normal thing. I think so I hope so you understood. Okay, so whenever we do tension test, we take up the critical fiber. Suppose complex data such as this one. So sigma 1 sigma 2 equal to sigma b, it means bending stress divided by 2 plus or minus root of this entire thing. Okay, so make the bending stress here and shear stress here, and you can just calculate each and everything. Okay, this is the basic thing. It means sigma 1 and sigma 2 principal stress. Okay, suppose if they ask about tau maximum, this is the basic formula. Okay, tau maximum equal to 16 divided by d cube root of m square plus of t square. Okay, tau maximum equal to 16 divided by d cube root of m square plus of t square. So after put your 5 values up there, and you can just find each and everything. Okay, so sigma maximum 16 divided by d cube m plus of root of m square plus of t square. Okay, see, if you want to make this as an equal, mean this 16 divided by dq m plus of root of m square plus of t square equal to 32 me divided by dq. Okay, 32 me divided by dq. Okay, so whenever you become m equivalent is m plus of root of m square plus of t square divided by 2. Okay, m plus of root of m square plus t square divided by 2, it is moment equivalent. Okay, so just now nothing, this if this is moment, this is also moment, and you can see this is moment equivalent. That's it. So not a bigger thing in principle. You're just going, we can directly understand below. Okay, you can just go to the next part. So whenever a movement equivalent is 1, the torque equivalent to root of m square plus of t square. Okay, this is the thing. Okay, suppose if they ask about the own versus stress, it means principal stress put here, and we can just calculate each and everything. Okay, so next one, type 2. Okay, combined law. Now what is being torque is given, bending moment is given, and axial. So like this, torque like this, bending moment like this, and axial like this. Okay, oh wow, so you can see this axial force also being given. So now here definitely what the two stresses will be. You can see stress equal to bending stress plus of this direct stress. Okay, this means as we apply the stress in axial stress also will be there. Okay, so I think so got the point. Suppose if I just want to apply, so the entire thing will be, this will be in torsion. Okay, so this one will be the definitely bending stress, or this will be the axial stress. Okay, you can see at each and everything here, you can see at neutral point here the bending stress and as well as the shear stress will be 0, but here the axial stress will be. Okay, so this is F and this is also F. Okay, top most and bottom most. Okay, top is only. Okay, here you can see here the shear stress will be like this, and the bending stress plus of direct stress will be. Okay, so now this is just now calculate the sigma 1 plus of, it means the maximum and minimum. So as I just told you about, so sigma x by 2 plus or minus root of sigma x by 2 the whole square plus of tau x by the whole square, this thing. Okay, so whenever we just get the answer, we can just go proceed on each and everything. Okay, I think so got the point. Suppose you can see this is the at the top point, you can see at the top point this is both are plus plus. Okay, but at the bottom while you are just going, you can see bending stress and it is opposite. So bottom it is different. Okay, I think so got the point. So sigma direct minus of sigma b, or anytime it means minus of anything can be. Okay, so at the axial you can say bending stress is 0, shear stress 0, only direct stress, no bending stress, no torsional stress. Okay, so now type 3. Okay, you can see torsion, bending moment, and axial compression. So now it's been compressed in a different way. Okay, now you can see minus p by a. Okay, so at the bottom you can see each and everything is done, but at the top you can see bending stress minus of direct stress is there. Okay, so take the same, it means top and bottom, you just calculate everything and you will get the record value. Okay, so not a bigger thing guys, not a bigger comparison. So I think so I can understand. So you can see this is torsion and this is temperature. Okay, so this entire thing is when this one the speeding is increased. So you can see whenever the temperature increases, this leads to compression, because when the temperature in the shaft just expands, so it leads to compression stress. Okay, whenever the stress increases, it leads to tension stress. Okay, so this is the entire thing. Okay, not a bigger case scenario, but I also understood. Okay, so next one is a comparison between hollow and solid shaft. So you can see hollow shaft is stronger than solid shaft. Okay, generally hollow shaft is always stronger than solid shaft by default. You can see same mass, same material, length, same area, same material, same everything same, and you can see diameter is greater than diameter of shaft. Outer diameter of the hollow shaft will be longer than the outer diameter of solid shaft. Okay, so as we are adding the same material, that's why this kind of thing is being there. Okay, suppose if we just take the same diameter, means generally solid shaft of the will be so much higher strength. Okay, you can see hollow shaft is always stronger than the solid shaft, but in industry we use solid shaft. Why? Because hollow shaft holds bigger area. Okay, You can see shaft rotates on the bearing. The solid shaft rotates on the bearing. Hollow shaft diameter bigger, so bigger bearing is needed. Okay, so that's why cost is so much high. But you can see solid shaft diameter small, so economically conserve. Okay, economically cost. Okay. And big bearing, you can see in the big bearing costly and friction loss will be more. So in industry, that's why we use rarely hollow shaft. So because outer diameter of the hollow shaft is longer and need a longer one size bearing. Okay, larger bearing, high initial cost and high friction loss. Okay, I think so can understand. So you can see here the entire thing we will just take average, but here you can see 0 to 100 like that it will be. Okay, so average stress, withstanding average stress is this one. Okay, you can see 70 megapascal. Here you can see it means hollow shaft the utilization of power is so much higher. Okay, so solid at the center it is given 100. Okay, this one not either. Okay, so what is the basic difference? Okay, you can see we are just going to compare the both of the thing. Okay, you can see strength comparison, same mass, same weight, same length and same material, each and everything is same. This is diameter of the shaft or solid, this is the hollow diameter. So you can see n equal to small n equal to d capital D divided by d. Okay, d equal to n of d. Okay, this is the maximum shear stress and this is the maximum shear stress of the hollow shaft. So you can see this is the tau max and 16 ds divided by ds. Okay, this one is okay. So whenever you just make it integration, it means whenever you just book it away, it means torque transmit in the whole divided by torque transmit in the shaft is entirely. While you're just doing this kind of thing, what will come this final answer. Okay, so hollow shaft transmits 44% more than the solid shaft. Okay, next to strain energy compression, you can see this is entirely the strain energy. So just a normal thing, you can see T square L by 2 GJ. Okay, you can see tau max will be 4 G into volume. This one little bit difference. Okay, I think so can understand, guys. So that's it. So not a bigger case, not a bigger problem. Just a simple thing. It means just an our understanding. That's it. Okay. So next one we will be sharing about theories of columns. Okay. So this I'll just discuss later on. So thank you for watching this video and have a good day.